What is a half adder? How binary addition works in hardware. Welcome to Gate in Kernel. Today, we are going to look at one of the simplest arithmetic circuits in a computer, the half adder. A half adder can add two binary bits using only two logic gates, an XOR gate and an AND gate. To understand why, let us start with binary addition. Chapter 1. Start with binary addition. Before looking at the circuit, consider every possible way to add two binary bits. Each bit can only be 0 or 1, so there are only 4 cases. 0 plus 0 equals 0. 0 plus 1 equals 1. 1 plus 0 equals 1. And 1 plus 1 equals binary 1 0. The last case is the important one. 1 plus 1 produces a 2-bit result. The right bit is the sum. The left bit is the carry. So a circuit that adds 2 bits needs 2 outputs, not just 1. Chapter 2. 2 inputs and 2 outputs. Let the 2 input bits be A and B. The half adder produces 2 outputs. S represents sum. C represents carry. So our question is simple: what logic should generate S and C? We can find the answer by examining all 4 possible input combinations. Chapter 3. The half adder truth table. There are 4 cases. When A is 0 and B is 0, sum is 0 and carry is 0. When I is 0 and B is 1, sum is 1 and carry is 0. When A is 1 and B is 0, sum is 1 and carry is 0. When A is 1 and B is 1, sum is 0 and carry is 1. This small truth table contains everything we need to build the circuit. Now let us examine sum and carry separately. Chapter 4. Finding the sum circuit. First, look only at the sum output. When A and B are different, sum is 1. 0 and 1 gives 1. 1 and 0 also gives 1. But when the 2 inputs are the same, sum is 0. 0 and 0 gives 0. 1 and 1 also gives 0. This is exactly the behavior of an XOR gate. So, S equals a XOR B. The sum part of the half adder therefore requires only one XOR gate. Chapter 5. Finding the carry circuit. Now look at carry. Carry becomes 1 in only one case, when A is 1 and B is also 1. That is exactly the behavior of an AND gate. So, C equals A and B. The carry part of the circuit therefore requires only one AND gate. Now we have both parts of the half adder. Chapter 6. The complete half adder circuit. The complete half adder combines one XOR gate and one AND gate. Both gates receive the same 2 inputs, A and B. The XOR gate generates sum. The AND gate generates carry. So the entire circuit can be described by only 2 equations. S equals a XOR B. C equals A and B. That is enough to add 2 binary bits. It is one of the simplest arithmetic circuits in digital electronics. Chapter 7. When A is 0 and B is 0. Suppose A is 0 and B is 0. The XOR gate outputs 0. So sum is 0. The AND gate also outputs 0. So carry is 0. Carry followed by sum gives 0 0. Therefore, 0 plus 0 equals binary 0 0. Chapter 8. When A is 0 and B is 1. Now A is 0 and B is 1. The inputs are different, so XOR outputs 1. Sum is 1. But both inputs are not 1, so an outputs 0. Carry is 0. Together, carry and sum give 0 1. So 0 plus 1 equals binary 0 1, or decimal 1. Chapter 9. When A is 1 and B is 0. Now reverse the inputs. A is 1 and B is 0. Again, XOR outputs 1. And outputs 0. So sum is 1 and carry is 0. The result is again binary 0 1. 1 plus 0 equals 1, exactly as expected. Chapter 10. When A is 1 and B is 1. This is the most interesting case. A is 1 and B is 1. 1 XOR 1 produces 0. So sum is 0. 1 and 1 produces 1. So carry is 1. Put carry on the left and sum on the right, and we get 1 0. Therefore, 1 plus 1 equals binary 1 0. Binary 1 0 is decimal 2. With only an XOR gate and an AND gate, the circuit has successfully performed binary addition. Chapter 11. Why is it called a half adder? At first, a half adder seems complete. It can handle every possible combination of a plus b. So why is it called only a half adder? Because multi-bit binary addition has another problem, the incoming carry. For example, imagine adding binary 1 1 and 0 1. Start with the least significant bit. 1 plus 1 equals binary 1 0. We write 0 in the current position and carry 1 into the next position. Now the next calculation is not simply 1 plus 0. It is 1 plus 0 plus 1. That third one is the carry from the previous bit. This reveals the limitation of the half adder. A half adder has only two inputs, A and B. It has no carry in input. So it can calculate a plus B, but it cannot directly calculate a plus B plus carry in. That is why it cannot serve as a complete adder for every bit of a multi-bit number. Chapter 12. Half adder versus real binary addition. The half adder demonstrates an important idea. Logic gates can perform arithmetic directly. Binary inputs enter the circuit. The XOR gate produces sum. The AND gate produces carry. There is no software inside the half adder. There is no instruction being interpreted by the circuit. Electrical states representing 0 and 1 enter the logic gates, and the gates produce the correct binary result. This is where arithmetic begins to emerge directly from digital logic. Chapter 13. From logic gates to computer arithmetic. The half adder is a tiny circuit, but the idea behind it is fundamental. Logic gates such as AND, OR, NOT, and XOR perform Boolean operations. But when we combine them in the right way, they begin to perform arithmetic. One XOR gate and one AND gate can add 2 bits. Real computers, however, need to work with much larger numbers. 8-bit, 16-bit, 32-bit, and 64-bit numbers. To add these numbers, carries must move from one bit position to the next. That requires a third input, carry in. Once we add carry in, the half adder becomes a much more useful circuit, the full adder. Conclusion. A half adder is the simplest digital circuit for adding 2 binary bits. It has 2 inputs, A and B, and 2 outputs, sum and carry. The sum output uses XOR logic. S equals A XOR B. The carry output uses AND logic. C equals A and B. So a basic half adder requires only one XOR gate and one AND gate. This tiny circuit demonstrates one of the most important ideas in computer architecture: arithmetic can be built directly from logic gates. But the half adder has one major limitation. It cannot accept a carry from a previous bit. To handle multi-bit binary addition, we need 3 inputs, A, B, and carry in. That circuit is the full adder. And that is where we will go next. Thanks for watching Gate and Kernel.